This video is going to talk about the mole conversions and stoichiometry section of your semester exam review. So, start off with is mole relationships, which are a lot of the questions in the mole conversion. So just converting from one thing to the other, that's going to come down to your mole wheel, and we'll talk about that here in a second. But these are questions like 14, 15, 16, and 17, where it asks you if you have a certain amount of something, is that more or less than or equal to 1 mole? So it helps to know what 1 mole is equal to. 1 mole is equal to a lot of things. So remember, 1 mole is just like it's just a counting number. It just means something that's really big. So just like a dozen is always 12, a mole is always a certain number of things. Specifically, it is 6.022 times 10 to the 23rd. Particles, things, atoms, we'll write part and we'll abbreviate it. But it is also equal to a few other things. So when it comes to just amount of a substance, 1 mole is always going to be equal to the molar mass of a substance. So taking the molar masses on the periodic table, adding them up, that's going to equal. So if we're looking at something like question 16, let me find my key real quick. If we look at question 16, where it asks, do I have more or less or eat 1 mole of 28 grams of magnesium? And the correct answer there, when I find my key, is more than. Because magnesium's molar mass is 24.31 grams. So when I look at magnesium's mass on the periodic table, it's 24.31, but I have 28 grams, so therefore I have more than 1 mole, because 1 mole is going to be equal to 24.31. Now, 1 mole is also equal to 22.4 liters of a gas. So that would be something like question number 17 that says I have 12.5 liters of nitrogen gas. Do I have 1 mole, less than 1 mole, or more than 1 mole? And when I look at a question like that, I'm going to say that I have less than 1 mole of nitrogen gas, because 1 mole is going to be equal to 22.4 liters. But 12.5 is clearly less than 22.4. And something like Avogadro's number up here, the 6.022 times 10 to the 23rd particles, that's, going to be question 15. So I have 1 mole of 1.65 moles of sodium, which means I'm going to have more than 6.02 times 10 to the 23rd atoms, because I have more than a mole, where 1 mole is going to be 6.022 times 10 to the 23rd. I have more than a mole, so I'm going to have more than that number of atoms. So those are our mole relationships as far as what we need to know and how much of something, just kind of looking at a problem, we would have. But we can also do that math, which this is something I would definitely have on my note card, something exactly like this. I know I gave you the mole wheel and we looked at the mole wheel too, and that'll help with stoichiometry, but this can too. But it also has, you can see it has the calculations you need to do to go from one side to the other and how you should set that conversion up. I know that some of you struggle with that and like how I should set it up, what number goes where. This can kind of help with that. Again, you have to know what order they need to go in, but just remember, matching up my like terms need to be diagonally from each other so that they cancel out when I do this. But I would definitely copy something down like this on your note card. If not, if it's the mole wheel, if it's this, whatever it may be, something like this to help you kind of with those conversions and to do them quickly. So now looking at stoichiometry, kind of that section, remember that's using our mole wheel. So kind of going from one side of the mole wheel to the other, using the balanced chemical equation. So we're going to look at a couple of that. So looking at 20A, we have the balanced chemical equation that was given to you. So we have calcium chlorate, KClO3, that decomposes or breaks down into 2 calcium chlorides and 3 oxygen gases. So it looks something like this. Now, 20A asks me, I need to calculate the volume of oxygen gas produced from decomposition of 75 grams of potassium chlorate. So, I'm starting with 75 grams of potassium chlorate. So now if you were looking at your mole wheel, we would say we have 75 grams of substance A. I know that I have that. That's the mass of A. I then need to go from my mole wheel down to moles of A, then from moles of A to moles of B, which in this case moles of B will be oxygen, and then from moles of B to volume of B. Now when I set this up, I'm going to make my pen smaller here. I'm going to start with that 75 grams of KClO3. That's where I'm going to start. So, now the first thing, to go from grams of A to moles of A, I need to use the molar mass, which I have 1 mole is going to be equal to our molar mass, which in this case, I should have had my key ready to go so I can answer this question. I don't. So 20. Calcium chlorate has a molar mass of 122.55 grams. So we can see that my grams are going to cancel out there. Then, from the balanced chemical equation, I need the molar ratio. That's how I go from moles of A to moles of B on my periodic table. Or on my mole wheel, sorry. And so in this case, in my balanced chemical equation, I have 2 moles of calcium chlorate. So 2 of KClO3. I really need to make more room. So 2 moles of that, which again, those are going to cancel out and give me, but also I have, for every 2 moles of that, I have 3 moles of oxygen gas, which is then going to allow me to go from moles of A to moles of B, and then go from moles of B to volume or liters of B, which remember that 1 mole of a gas, like oxygen, is equal to 2.4 liters. I hope none of you are yawning. So, then all of my units are going to cancel out. So I've canceled out my grams of calcium chlorate. I've canceled out my moles of calcium chlorate. I've canceled out my moles of oxygen gas to leave me with liters of oxygen gas. And when I do that calculation and multiply all that straight across, I'm going to have 20.6 liters of oxygen gas. So again, remembering how to set that up and going straight across with that and setting those up kind of in the correct. Now, using the same chemical equation, in 20B, I need to calculate the mass of potassium chloride produced from 75 grams of potassium chlorate. So now I'm going from grams of A to grams of B through the mole wheel, if you have that out in front of you. So to start, again, I'm not going to rewrite the equation this time. I'm going to start with 75 grams of calcium chlorate. I'm going to try to write this a little nicer too. So I started there. Now, just like before, take my molar mass. I have 1 mole of KClO3, potassium chlorate, and for every 1 mole, I have the molar mass of potassium chlorate, sorry. So KClO3. Then that's going to be not equal to, but I'm going to multiply that then by the molar ratio of potassium chlorate to potassium chloride. So I have 3 moles of KClO3 in my equation. And for every 3 moles, I get only 2 moles of potassium chloride. Which then, going from, now I'm going to be left with moles there of potassium chloride. So I then need to take the molar mass to get grams of potassium chloride. So 1 mole of potassium chloride is going to be equal to the molar mass, which is going to be 74.55 grams of KCl. So just like before, my grams of potassium chlorate are going to cancel out, my moles of potassium chlorate, and my moles of potassium chloride, leaving me with grams of potassium chloride, which in the grand scheme of things is going to be equal to 45.6 grams of potassium chloride. Ta-da! So, this will go to 23 A, B, and C, so the eliminating reagent problems. So, to do this, we have the balance equation. So, 2 nitric oxides, so NO, and 1 oxygen gas will form 2 nitrogen dioxides. Now, I've already drawn the pictures. That was part A. So to draw 4 nitrogen oxides molecules and 4 oxygen molecules on the reactant side. Now, that's how many I have. So I'm looking back at my balanced equation, which I can write on here, that we have 2 nitrogen oxides and 1 oxygen gas give me 2 nitrogen dioxides each time. So when I look at my equation, I'm going to use, I guess I'll use green here to circle everything. Now we'll use red. So this is basically up here, up top here. This is my recipe. So to make what I need to make, I need 2 nitrogen oxides and 1 oxygen gas. Then I can do that again. But I am now out of nitrogen oxide, monoxide. Now, what I then need to do is draw all those over here. So for each one of these bubbles, I get 2 nitrogen dioxides. So nitrogen is the brown one. And we'll do that again. So I'm going to get 4 of these eventually because I have 2 bubbles over there. And I need my green circles here. 1, 2, 2, 1, 2, 1, 2. So therefore, I get my 4 nitrogen because I did this recipe 2 times on the left. So therefore, I'm going to make 2 batches of this. So every time I make a batch, I get 2 nitrogen dioxides, which I'm left with over here. So my limiting reagent in this problem, my LR, is going to be the nitrogen monoxide because I used all of that up. My excess reagent, what I have left over, is going to be the O2 because I still have a bunch of O2 over here. And that's it. So that's that problem there. So my limiting reagent is nitrogen oxide, and my excess reagent is the oxygen gas. So again, the key is drawing the picture correctly so that you use the appropriate amount of your reactants to form the products and drawing the circles around them.